This next one is my favorite problem of the entire year. It's called the magical reappearing integrand. TM. So this, on first glance, might look a little bit like the last example we saw, where it looks like the integral of one thing and like, oh, he's just going to do that trick where he calls sine squared, the first product, the first factor, and d theta its own factor. Well, we could, but looking ahead, I'd run into problems here because although d theta is certainly easy to integrate, so it would make a great candidate for dv, sine squared of theta would make a terrible u because although I know how to take its derivative, it doesn't get simpler when you differentiate it, right? The derivative of sine squared of 2 theta would be 2 sine theta cosine theta, which now that I think about it is also sine of 2 theta. So it actually might work that way. But nonetheless, we're going to do it a different way. What we're going to do instead is break the sine squared of theta up into two different factors. We're going to think of this as sine of theta times sine of theta d theta. So if you're thinking to yourself, well, how am I going to choose which one is the u, which one is the dv? Well, that was a silly question because they're the same thing. Sine of theta and sine of theta, doesn't really matter which one's which. One of them's going to be the u, the other's going to be the dv. So the derivative of sine is easy. So easy that I messed it up right there. The cosine of theta d theta. And the integral of sine is also pretty easy. Of sine of theta d theta is also pretty easy. That one is negative cosine of theta. And there's no reason why you would have to use theta here and not x. Usually when we're talking about angles, we stick to theta, but you could call it x if you prefer. And so we can set up our integrand here. And I can't stress this enough. I should have stressed it earlier in these videos. Writing this half of the integrand is incredibly important. More in this problem than in any other problem we do today. And you'll see why in a minute. But when you do integration by parts, it is really important that when you apply the formula for integration by parts, you start with the integral of u dv. Start with this part, and then you can do the other half of the formula. uv, so negative sine theta cosine theta, minus the integral of v du. So the minuses cancel each other out. V du would be cosine theta times cosine theta d theta, so cosine squared theta d theta. And here we're going to do a little trick. Now, you might say to yourself, oh, so now we have the same situation where we can do the cosine theta as the u and another cosine theta, d theta is the v, and you know what, that might get you somewhere. But I have a more fun trick to try. We also know that whenever we start seeing sine squares and cosine squares in the same problem, we can always use the Pythagorean identity to kind of rebalance that and put them back the way we want. So what I'm going to do is take this sine squared of theta and leave it alone, and take the cosine of theta, which is in this integral over here, and rewrite that as 1 minus sine squared theta. We know that's one of the Pythagorean identities. 1 minus sine squared theta. And remember, that's all the integrand, so that can be grouped together. And we know that when we have the integral of a difference, or a sum, we can split that up. So I can take that last bit there, the integral of 1 minus sine squared theta d theta, and write that as the integral of 1 d theta minus the integral of sine squared of theta d theta. Well, part of that is super simple. So why don't we do them in two separate parts? We'll do the easy part first. The integral of d theta, the antiderivative of just d theta, it's like the antiderivative of 1, that's just theta. But what to do with this minus sine squared, integral of sine squared of theta d theta? You might look back at the beginning and say, oh God, we're back where we started, so we have to do this all over again? And the answer is no, we're back where we started. This is why we call it the magical reappearing integrand. When we see the integrand appear again, as long as it's not also a simple positive integral of sine squared of theta d theta, as long as it's anything other than that, if we see that integral again, we can move it over to the other side. We can combine that with the integral of sine squared theta on the other side. And this is why, in this problem in particular, it is so important to have written the integral of v du on the other side, because we were going to need it. Now we can add them together. The integral of sine squared theta plus d theta plus the integral of sine squared theta d theta is two of them. 2 times the integral of sine squared theta d theta. And we know on the other side, we are free of any integrals on the other side. I do have a slight problem that since I no longer have an integral on the other side, the shortcut I mentioned earlier in the first video of not bringing up the c could come back to haunt me now. I need that c. I'm taking in an antiderivative. I've taken an antiderivative already. There is a constant of integration. I was ignoring it before because I knew I was just going to integrate and end up with a c later on anyway, so I was just saving for later. But that's gone now, so I need to make sure to remember the c. And remember what we were trying to do all along. We were trying to find the antiderivative of sine squared theta d theta, which I still don't know what it is, but I do know what 2 times the antiderivative of sine squared of theta d theta is. So naturally, if I want to know what the plain old integral of sine squared theta d theta is, I'll just divide everything by 2. And what we're left with is the plain old integral of sine squared theta d theta, and it's equal to, feel free to separate these into different terms if you want, but I don't see much of a reason to. I'll put the plus c at the end so we notice it. And that is the story of the magical reappearing integrand.